All right, so welcome to the video lecture series on Introduction to Computer Networks. This is part 4 of our lecture topic on wireless LANs. So we'll jump to the point where we left off. All right. So it's very common in a wireless network to have multiple wireless hosts and access point communicating with multiple wireless hosts at the same time. So in that scenario, the wireless link protocol needs to facilitate or ensure that there are no or at least less collisions when two nodes are actually transmitting at the same time over the same frequency. So we have already established at this point that one access point will operate only over one channel, that is one specific frequency. So if there are three wireless nodes which are connected to that single access point, it's very common to have a scenario where two nodes will be requesting to send something to the access point at the same time. So to avoid that, to avoid the collision, wireless protocols incorporate something that we call the CSMA/CA technology. So CSMA stands for Carrier Sense Multiple Access. All right, so this part of the name refers to the fact that wireless networking technology allows to sense the frequency at a given time. So when we say sense, it means that it can listen to that particular frequency and know if that frequency is busy or idle at a given moment of time. The second part of the name, CA, refers to collision avoidance, which means that we will try to sense the frequency, and then using that knowledge, we will try to avoid any collision. So CSM allows hosts to sense the channel for traffic. That means it needs to, it can know if the frequency is busy or idle at a given time, and it needs to know the condition of the frequency before it starts to transmit, or even if it before it requests to transmit something. However, it may actually be difficult at times to to receive or sense the frequency before the transmitting because of signal fading, which means in formal terminology we call it signal attenuation, and that is if the signal is actually weak, it may not always give you the correct information. Additionally, it cannot sense all the collisions at any case because there are other problems which we have seen. For example, the hidden terminal problem, the exposed terminal problem, and also the fading and interference limitations of wireless links. So the primary objective of CSMA/CA is don't collide with any ongoing transmission at a given time, and we try to do our best to avoid that. So let's see how that works out. So first, if a sender is trying to send something to a receiver, it will first use CSMA, the Carrier Sense Multiple Access technology, to sense if the channel is idle. It will continue this operation for a particular duration of time, and that we refer to as the DIFS, or the DCF interframe spacing. So given that the sender senses the channel is idle for this duration of time, only after that it will start the transmission. So that means it will try to detect if there is any possibility of collision, and then it will, if it succeeds in finding that the frequency is free, only then it can avoid collision and starts transmitting the entire frame. However, if the sender using CSMA senses that the channel is currently busy, what it does is that it starts a random back off time. So that means that it starts a random timer, so let's say 5 seconds or 3 seconds, and it waits for that time. So as the timer counts down, it waits, it doesn't do anything, it waits for the frequency to get free, and when the timer expires, it then starts the transmission. So whenever it is waiting for some time, it is actually assuming, the sender is assuming that the channel has become free after that point, and then it starts the transmission. However, in case it does not receive any acknowledgement of the receipt by the receiver, it increases the random waiting time. So before, let's say in the first phase, it senses that the channel is busy, it waits for 3 seconds, transmits the data, does not receive an acknowledgement. So then it will increase the random waiting time to, for example, 7 seconds. So it waits now for 7 seconds and then tries to transmit again and waits for the acknowledgement. So this process repeats as long as it does not successfully receive the acknowledgement. On the other hand, the receiver, if the received frame is okay, which means that if there are no corrupted bits whatsoever, it has received all the required parts of the packet which were being sent, and if the transmission goes through okay from the sender to the receiver returns an ACK to the sender. However, the ACK is sent after a small duration of time that is called the SIFS, or the short interframe spacing. So this duration of time is a waiting time at the receiver end to just make sure that it does not overlap the ACK packet with any other immediately waiting transmission in its network. It just needs to make sure that the ACK is received by the sender. So it just waits for some time, makes sure that the frequency is free, and then quickly sends out the ACK to the sender. So the technology that we just saw, the protocol that we just saw, allows the collision to be detected before it's transmitting, and then transmits whenever it finds the channel to be free. However, we can completely avoid any possible collisions using a related concept that we call channel reservation. So the idea is that a sender will first try to reserve a channel by sending out reservation packets, and once it is guaranteed the reservation, it will then start the transmission. Eventually, this results to a complete avoidance of any possible collisions, particularly in the case where the data frame which is being transmitted is significantly long, and some other nodes may possibly start transmitting in the middle. So to avoid data corruption in those cases, reservation is greatly beneficial. So what happens is that the sender first transmits what we call RTS packets. It stands for request to send. So the RTS packets are sent to the access point using carrier sense multiple access technology. So it first senses if the frequency is free or not. If it is free, it will then send out an RTS packet to the access point. Do note that RTS packets may still collide with each other. That means node A and node B can send an RTS packet to the access point at the same time, which means that both of them will be discarded. So however, they are short, so they can be retransmitted at short intervals. So when the RTS packet is sent, an access point, if it receives the RTS packet successfully, it responds with what we call our CTS packet. This stands for clear to send, and this is in response to the RTS, but we will see that CTS is sent out to all the other wireless nodes. So when all the other nodes receives the CTS packet from the access point, they know that they are now not allowed to send or receive any data over that particular frequency. So once the sender receives the CTS from the access point, it then knows that the channel has been reserved. The sender then can start transmitting the data frame, and all other hosts will now need to wait. So let's look at a simple sequence of the RTS-CTS process. So first, node A and B send the RTS, the request to send packet at the same time to the access point, and they collide, and both of them are discarded. So both of them will now wait for a random back of time, and whichever one gets timed down first will get to send the RTS. In this example, A gets a chance before B, so A then starts, sends out the RTS to the access point. It is broadcasted over the same frequency. The access point receives the RTS packet, and when it successfully receives the RTS, it sends out a clear to send announcement to all the nodes which is within its range. This implies that every other node which is within the connectivity range of access of the access point now needs to wait until A finishes its transmission session. So when A receives the clear to send packet, A can now start transmission of the data, and access point receives that, finishes the transmission, and once that is completed, the access point will now send out a broadcast acknowledgement to all the nodes, which can also imply that A has finished the transmission, so anyone else who would now want to request can send their request to send packet. And at the same time, A, when it receives the acknowledgement packet, will now know that whatever data it has sent to the access point was received successfully. So the common wireless standards under the IEEE 802.11, the first version was 802.11a and B, and as you can see, they operate in slightly different ranges. So A operates in 5 to 6 gigahertz range, while the version B operates in 2.4 to 5 gigahertz range. The max speed of A is up to 54, while the max bandwidth of B is up to 11 megabits per second. However, version B was actually more popular because it has something that we call the DSSS, which stands for Direct Sequence Spread Spectrum, and this allows the interference to be reduced. So this is an additional technology with 802.11b had, and which made it actually more popular than version A, although A had a higher bandwidth. There are other versions, the version G, which is very similar to version A in terms of the range. It's similar to version B, but the speed is actually higher than A, so it came up as a combination of the best properties of version A and B. Recently, the more common version of the wireless network is 802.11n, which allows access points to have multiple antennas. And when you have multiple antennas, That means that it needs to have a specific type of property or feature that we call MIMO, which is multiple input, multiple output. So the version N can operate with multiple input and multiple output mode with the use of multiple antennas, and works in a 2.4 to 5 gigahertz range with a max bandwidth of 200 megabits per second. And then the final version, which is the high-speed wireless LAN, it also has multiple antenna, but now it has a much higher capacity, and it can also support multiple user with these multiple antennas. So that's why we call it MU-MIMO, which means multi-user, multiple input, multiple output. And as you can see from the speed comparison, they can go up to 300 gigabits per second. So this is very high-speed wireless network. And for that, we can support multiple users. And with the use of multiple antennas, we can have multiple input and output at the same time. Just a quick note that all of these standards, they support the CSMA technology that we just saw earlier for collision avoidance. And all of these versions have both the base station or the infrastructure mode and the ad hoc mode versions.